Hi, I'm Kyungmin from Postec. This is joint work with Hyunji Kim and Professors Ujin Han and George Fletcher. Our present early, which combines sampling and synopsis for primary estimation in graph data. Given a core graph and a data graph, the cardinality is defined as the number of all embeddings of the core in the data graph. For example, here the cardinality is 100. Our problem is to estimate this cardinality in an accurate and efficient way. Estimate can be used in best approximate code processing if the user is satisfied with approximate answers and want to save time. The estimate can be also used for query optimization in graph databases. Given a pattern matching query, a cost-based optimizer enumerates various subpairs using dynamic programming and computes the cost for each subpair. The cost model calculates the cost based on the estimated cardinality. Therefore, fast and accurate estimation is necessary to select a good plan with small optimization time. In general, there are two approaches to solve the problem: sampling and synopsis. Sampling-based methods perform sampling, assign weights to samples, and aggregate this weight to estimate the cardinality. Synopsis-based methods produce summary structures and use the structures to perform online estimation. Among all this, Wonderjoin, a sampling-based method, was shown to be most accurate in our previous benchmark paper, GPA. However, Wonderjoin suffers from large sample space due to at-zero time sampling. First, let the sampling order of courages as follows. For the first courage AB, 101 data edges can be sampled. Only one blue edge can lead to an embedding. Other 100 red edges here lead to sampling failures, which means that no embeddings of the core can be sampled. Since Wonderjoin is a Horowitz Thompson estimator, estimates are zero for fair samples and inverse power test for other samples. Overall, the estimate is unbiased, but it will mostly suffer from underestimation and the variance will be extremely large. We formally define this as follows. Let Zi denote the estimate of I sample, Si. Z is the average of Zi's over n samples. N is the set of all embeddings, so its size is the primary. And P is the set of all partial embeddings that can be sampled, which is the sample space. Then the first equation says what I just explained in the previous slide. And the second one says that variance is roughly proportional to the size of sample space. The third equation says that you can use the variance by increasing sample size, but it comes with a time cost. So it's important to reduce sample space in the first place. Now we propose another method that combines sampling and synopsis. At the online phase, we use another sampling strategy called random walk intersection to reduce the sample space. We use branching to further reduce variance. However, sample space can be still large. To further reduce sample space, we index the domains of small parents as synopsis. A domain is defined for each pattern vertex, which is a set of all data vertices that participate in an embedding of the pattern and match that vertex. Then, these domains can be used as candidates for larger queries that contain these patterns. This reduces sample space and increases estimation of this. However, when computing domains, we don't know which patterns will be recorded online. Another way is to compute the domains for all possible patterns that appear in the data graph, which is infeasible. To solve this problem, we detect tangle patterns, which are hard to estimate by sampling, and compute the domains of tangle patterns only. We use another walk better than calculate approach. Without discussing each in detail. First, random walk intersection with the sample of vertex at a time. We select the sampling order of vertices, for example, A, B, C, and D. Then the candidates for these vertices are obtained by intersecting the candidates of all incident edges. For example, to obtain the candidate for A, we intersect the candidates for A, B, and A, C. Then we obtain only one candidate here, then match A. For subsequent vertices, we also intersect with the neighbors of only the sampled ones. So here, to obtain the candidates for B, we intersect the candidates for BC and the neighbors of A who have labeled B. If there are many candidates left, instead of sampling just one vertex, we sample multiple times to reduce the variance. We call it branching. Here, since C has many candidates, we sample some portion, say 10 out of 100 candidates. And this shows our sampling path. The branching generates multiple samples with a common prefix for A and B, and branches at C. To perform estimation from these samples, we assign a weight to each test node and recursively aggregate bottom up. First, leaf nodes have weight as the number of candidates if the sampling has succeeded, or 0 if the sampling has failed. Internal nodes average the children weights and also multiply with the number of candidates. The root weight is the final estimate. Note that we can make multiple trees if the sample size is given enough. Then we just average these root weights. However, as you may expect it, one intersection may not prevent all sampling failures. For this new data graph and for vertex A, intersecting the candidates for A, B, and C cannot print 1,000 labels here that lead to sampling failures. To solve the problem, we index the domains of small patterns. The concept of domain comes from frequent subgroup mining, where the domain of a vertex U of a pattern P is a set of all data vertices that participate in an embedding of P and match U. For example, for this triangle pattern P and its vertex A, the domain consists of a single vertex A here, which is in a triangle, and match A here. Domains can be used as candidates for cores that contain these patterns to the anti-monotone property. This property tells that if P is a subgroup of Q, then the domains of P are supersets of the domains of Q. Therefore, the domains of P can be used as sample candidates for Q without false negatives. For example, if we have indexed the domains of this triangle pattern, we directly obtain one candidate for A that participates in a triangle, and safely discard 1,000 candidates that lead to sampling failures. If the diameter of P is larger than 1, then using the domains of P is much better than using one of intersections only. Furthermore, domains can reduce intersection overhead where the intersection is the top bottleneck. For example, if C is the starting vertex, the candidates for C can be obtained by intersecting the candidates for CA, CD, and CD. However, using the domains of P and C, we can replace the first intersection with the domain. Since the domain is a subset of the first intersection by the definition, the sample space can be reduced. Then, at the offline phase, which patterns should we index? Computing and indexing the domains of all possible patterns is infeasible in terms of time storage. Since our focus is to reduce the sample space for hard patterns, we index such patterns only. We call them tangles. Here, triangle is tangle, while this wedge is not. We call the resulting index as tangle pattern index, TPI, where the former definition increase hierarchy. To build the index, we start from small to large parents up to a certain size, as in typical frequent sublet mining. To detect tangle parents, we interrupt sampling with indexing, which require work better than careful approach. Given a larger pattern, we perform sampling using the domains of smaller pattern. For example, 2 uses the domains of P1, P2, and P3. If sampling varies a lot, we index Q as a tangle pattern. Here, note that the domains of Q are subsets of the domains of P1, P3. And otherwise, if sampling does not vary, Q is untangled. We just treat the domains of P1 to P3 as the domains of Q. So, for a larger pattern that contains Q, it uses the domains of Q as template, which is actually the domains of P1 to P3. This way, if sampling succeeds for most patterns, domains can be reused up to much larger patterns, and only few patterns will be detected as tangled. We can skip indexing a lot of these patterns. Our approach has 5 components. First, expensive domain calculation can be reduced with cheap sampling experiences. Second, if a pattern Q is tangled, then its domains will be much smaller than the reference domains in sampling. This has the effect of bounding the index size, similar to using a discriminant ratio in the previous paper. Third, to increase online accuracy of LE, we allow LE itself to determine higher cases of bind. Fourth, we can control the offline overhead and online accuracy of our index by changing the threshold for failure rate. Finally, our index can be added to other sampling-based methods, which would be interesting feature. In practice, we optimize indexing with the following techniques. First, we use dynamic crawling to compute the domains instead of running MPR sublet matching. This gives a linear time complexity for 3 patterns. Second, we group labels to reduce the number of patterns to consider. Third, we stop random walk if the failure rate converges as quickly as possible. Now we back to online estimation after building our index. Here are the remaining details. First, how we search for the domains of patterns of online fields. Given a query, there can be an exponential number of sub-patterns that are indexed. So search for the domains of all patterns may become a large problem. Therefore, we use a greedy and recursive approach to search for sub-patterns that are more likely to reduce the sample space. Given a sampling order, we search for a pattern that covers the first tables in order and have the smallest domains. Next, we remove these tables and use the remaining query as a new input to the next recursive query. We show that this algorithm has a time complexity quadratic to the query size. Second, we also use a greedy approach to determine the sampling order. We define a length for each vertex view as the minimum selective of candidates of incident edges. We choose the minimum length vertex as the starting vertex. For a time, we use the other 2 lengths. For the remaining vertices, we keep selecting the vertex that has the largest number of connections to the selected ones. For a time, we again use this length. We implement intersections by referencing empty heading without using its data comparison techniques. Our data model stores the projected edge candidates for all labels appearing in the data gap, and the neighbors of each data vertex with a label. These are stored in sorted and contiguous arrays. Given n such arrays, we perform pairized intersections from the smallest arrays. This takes time linear to the smallest array size. In our pattern, LE also has theoretical boundaries. Here, Z and Y denote the random variables for our estimate, where Z is the average of multiple Ys. LE can guarantee certain accuracy with any relative error bound epsilon, and confidence threshold mu always in all agent time. Here, LGM is called the worst-case optimal bound for granularity. Proofs using the three propositions are shown in our technical paper. Here are some current results. We use 6 datasets with parent statistics. For the first 4, we use the same queries in our previous benchmark paper. For other 2 datasets, we use the same queries in a sub-matching benchmark paper that use these datasets. LE and LE plus PPI denote our method without and with indexing respectively. The top figure shows mean Q error for given queries, and the below one shows contours of distributions of Q errors for human dataset, where we differentiate the under and overestimation cases. The x-axis shows particulars, and you can see that our methods have near 1 Q error, which means that estimation is almost perfect. Our methods outperform all others for all cases. For larger queries up to 32 bytes, our methods still have much smaller Q error, closer to 1. Others suffer from significant under or overestimation. Ours also have similar or better efficiency than other sampling-based methods, with 1 millisecond runtime on average on these 2 methods. We also perform an evaluation study of our indexing approach, where x-axis is max pattern size to index, and the y-axis shows the measures. In each cell, the right side shows the result for the naive approach indexing or possible patterns, and the left side shows the result of our work-varied and calculated approach to index tangle patterns. You can see that index time and storage can be reduced up to 56 and 9.7 times respectively. This shows that our indexing approach is as effective as the naive approach. Both LE plus TPI and LE plus naive show higher accuracy than LE without using an index. Overall, at the online phase, combining sampling with synopses can increase the sampling accuracy. At the offline phase, interleaving the sampling with indexing can increase indexing efficiency, while preserving the effectiveness of online estimation. To conclude, LE is a fast and accurate dynamic estimator for graph data that combines sampling and synopsis. We propose random walk intersection to reduce sample space. We also propose walk, build, and calculate approach that integrates sampling during indexing to detect tangle patterns and increase the indexing speed. We also show that LE has theoretical guarantees of estimation quality and runtime. Finally, we show that LE has much higher accuracy than existing methods, but has similar efficiency. For future work, you may apply the walk, build, and calculate approach to other sampling-based methods, and it will reduce intersection time with VMAPs or SIM or even GPU operations. And we can easily utilize within our index and sampling, where we only use a single cycle. Thank you for listening.